Hello all, good evening. Welcome to my YouTube channel All About VLSI. Hope you're all doing good and I hope my voice is audible and my screen is visible, right? Yes. So let us start our session. So before going to start our session, please make sure that subscribe to our channel All About VLSI if you haven't subscribed, right? Yeah. So let us start today's session, analog electronics session. So today's topic is diode approximation models. Okay, so we will see what are these diode approximation models in solving our problems related to diode circuits, right? Okay, so we will see how to approximate the diode. Okay, so yeah, so let us briefly see what we have discussed in our previous sessions. We have started with the what is meant by semiconductors, and we have seen what are meant by diodes, what is meant by PN junction diode, how is a PN junction diode is formed, and we have seen the forward bias and reverse bias conditions of a PN junction diode, and we have seen how to draw the VI characteristics and what is the relationship between the voltage and current of a diode which is in forward bias and reverse bias that we have already seen in our previous session. Okay, so if you haven't watched those sessions, please go back and watch them, so because they are very important to understand this particular topic. Okay, yeah, now let us start with the diode approximation models. Okay, now let's see the diode approximation models. So there are two models basically. One is called ideal model. So we'll start with the ideal diode model. Okay, we will start with ideal diode model. So what is this ideal diode model? So in the case of ideal diode model, let us consider a circuit. Okay, so let us consider a circuit where we have a control resistor R which is connected in series with a diode. Okay, and this diode is biased in a forward bias fashion. Okay, this diode has been biased in a forward bias fashion. Okay, so how I am saying it is forward bias, since the positive side of the voltage is connected to anode and the negative side is connected to the cathode, so it is a positive bias diode. Okay, I think up to here it is clear for everyone. Now, so let us say this is anode and this is our cathode. Okay, and the voltage across this diode, let us say it is VF, that is forward voltage. Let me write it here. VF is the forward voltage. VF is the forward voltage, and the current flowing through this diode and through this circuit, let us say it is IF. Okay, so IF is the forward current. Okay, IF is the forward current. Okay, so what is the diode is in? So the diode is, it is in forward bias condition, and the current flowing through the diode is in IF, and the voltage across this diode is VF. Okay, so the ideal model of a diode is a least accurate approximation. So this ideal diode model is a least accurate, it is not so accurate model. Okay, so but for understanding we are going to discuss it, and it is in this case of ideal diode model. In the case of ideal diode model, the diode is considered as a switch. Okay, the diode is considered as a switch. I will write it here also. Considered as a switch. What it is considered as? In the ideal diode model, the diode is considered as a switch. You know the switch, right? So if we let me draw it for you. So in the ideal diode model, it is considered as switch. So the equivalent circuit for the ideal diode model will look like this. So this is our resistor, this is our power supply, and instead of drawing our diode, we will draw a switch. I hope you are aware of what is meant by switch and what is the diagrammatical representation of switch. Okay, so this is the diagrammatical representation of a switch. Okay, this means this diagram means the switch is off. Sorry, the switch is on. The switch is on means the circuit completes. That means it is a short circuit condition. That is, it means it is in short circuit condition. And the switch, if it is off, then what happens? It will be represented like this, like in a open circuit manner. Okay, so when the switch is off, it cuts the circuit, or it is in a open circuit manner, or the circuit is in open circuit. And here, if the switch is off, that is if the if the switch is on or it is closed, then it is a closed circuit. It is making the circuit, that is the current will pass through this circuit if the switch is on, and the current will not pass through this circuit if the switch is off. This is obvious fact, we know that from our childhood we are studying that, right? So if the switch is on, the current will flow through the circuit, and if the switch is off, the current will not flow through this circuit. This is clear. Okay, so this is the diode approximation, nothing. Okay, so for finding the why we are using this diode model, diode approximation models, why we are actually discussing about this. Okay, so the agenda for discussing this diode approximation models is nothing but to understand the voltage across the diode, that is a forward voltage, and the current flowing through the diode. So to find out what is the voltage across this diode and what is the current flowing through this diode, to find out this, we are going to use this diode approximation models, or we are going to use this diode approximation techniques. Okay, so from our childhood or from our 10th standard, we are studying how to find the voltage if we have given a simple power supply like this and a resistor if it is given, or if we have a chain of resistors or capacitors and let's say inductors if we have, or RLC circuits if we have, then we know how to find the voltage across a particular resistor or particular node, how to find the voltage and how to find the current at a particular node and how to find the voltage at a particular node. That we already know the techniques. We can use Kirchhoff law or other laws which are present to find the voltage or current which is flowing through this RLC circuits, resistor, inductor and capacitor circuits, right? But if we are having a diode, then how to find the voltage or current flowing through this diode? We should model it to some known models, right? Like for, okay, that how to model, we will see that. Okay, so in this case of ideal diode model, what we are considering, the diode, it as a switch. Okay, so if it is on, then it is a closed circuit, and if it is off, then it is a open circuit, right? I hope it is clear up to this point. Okay, it is clear. Is it clear? Now what we have seen in forward bias condition, so we will discuss this forward bias condition and we will come back to reverse bias condition. Okay, so if you're having any doubts or queries, you can just simply ping in the chat. I will try to answer your queries. Okay, yeah. In forward bias condition, what we have discussed, if external voltage is greater than the barrier potential 0.7 volts, then our diode start conducting. That is, the diode will allow the current through the, okay, the current is allowed through the diode to flow. Okay, the current will flow through the diode. That we have seen in our previous sessions only. Okay, now we will consider our external voltage is greater than 0.7 volts. Okay, so in this case, let's say this is our resistor and this is our external voltage, V external, and this is our diode. Okay, we have, so it is in forward bias voltage, and let us assume that we have given enough voltage so that diode is turned on. Okay, the diode is turned on. So how to represent the diode is turned on? We will represent it in the switch model or ideal model using this representation. Okay, using this switch representation. That is, the switch is closed. That is, the diode is conducting, so the diode is allowing the current to flow through it. The current is in this direction. Okay, minus to plus forward current, IF. Okay, So the diode is conducting the entire current. So in the ideal diode condition, what we are considering, there is no resistance at all. There is no resistance offered by the diode at all. There is no resistance offered by the diode to the current. Okay, there is no resistance offered by the diode to the current at all. The diode is conducting entire current. Okay, IF is flowing simply through this diode. There is some external resistor which is present. This is we have kept externally, but the diode is not offering any resistance to this current which is flowing through the diode. Okay, in which condition? It is a ideal condition. This is the ideal approximation model. In the ideal approximation model or ideal condition, what is happening? The diode is not at all offering any resistance to our current, forward current. Okay, so the current is flowing without any without facing any resistance through the diode. So this is about in ideal condition forward bias. Okay, so this is how we should draw the model of diode in the forward bias condition for ideal condition. Okay, so this is the ideal approximation model for forward bias. Now let us see the ideal approximation model for reverse bias condition. Okay, for reverse bias condition. Now in the case of reverse bias condition, again we will see the external resistance and the voltage supply, negative, positive, negative, positive, right? And we have our diode. So this is our diode. How I am saying it is a negative bias condition? It is in negative bias condition. This is negative side and this is positive side, which is connected to anode, and this is connected to cathode. So this we have already discussed in our previous session, how to bias a diode in negative, right? How to bias a diode such that it works as a negative bias diode. Okay, that we have discussed in our previous session. Now how to model this? Okay, how to model this? What happens in negative bias condition? The diode will not at all conduct. Okay, so in negative bias condition, in negative bias, or sorry, reverse bias condition, in reverse bias condition, no current will flow through the diode. No current will flow through the diode. So what is this statement? It is a ideal statement. So in an ideal reverse bias condition, no current or zero current will flow through the diode. Okay, so in ideal conditions only, but practically speaking, a small amount of leakage current is flowing, but ideally speaking, there is no current flowing through this diode. Okay, so ideally speaking, there is no current flowing through this diode. So how to model this? How to draw this? So it can be drawn like this: power supply with a open circuit, Okay, so what it represents? No current is being flowing through this diode. Okay, why? Because it is an open circuit, right? So no current is being flowing through this diode. Okay, so in reverse bias condition, this is how we are going to model a diode for the ideal approximation. So this is the ideal approximation of a reverse bias diode. Okay, yeah, so I think up to here it is clear. Now let us find the voltage and current. Okay, so first let us draw the VI characteristics of this diode in forward bias and reverse bias in the ideal approximation. Okay, so let me write it here. VI characteristics of diode in ideal approximations. Okay, let us see the VI characteristics of the diode in ideal approximations. So how to draw the VI characteristics of the diode in ideal approximations? Let's see. So here on the x-axis I will draw the forward voltage VF, and on the y-axis I will draw the forward current IF. Okay, so this is reverse voltage VR. Okay, so in the ideal approximation, sorry, previously made some wrong statement. So previously I have made some wrong statement. So the correction is, in ideal approximation, what happens is, in ideal approximation, we are assuming, so ideally speaking, what we are assuming is, at external voltage, if V external is 0 only, then the current, forward current will flow through our diode. Huge amount of forward current will flow through our diode. So this is the approximation we are going to make in our ideal approximation. Okay, so our VA characteristics curve will look like this. So at 0 voltage only, forward voltage only, so VF, and here we have a high current. Okay, next, at reverse bias there will be no current at all. So how much you apply the voltage, the current will be equal to 0, ideally speaking. Okay, so this is the VI characteristics curve of a ideally approximated diode. Okay, ideal approximated diode. Okay, so the VI characteristics curve depicts the ideal diode operation, since the barrier potential and the forward dynamic resistance are neglected. So in the ideal approximation, barrier potential and dynamic resistance are neglected. Dynamic resistance are neglected. This is what we are doing in the case of ideal approximation of a diode. Okay, so here these two are neglected, and the diode is assumed to have a 0 voltage across it when it is biased. Why it is having a 0 voltage? Since it is short circuited, so there will be 0 voltage across this diode. So V forward will be equal to 0 volts. Okay, the voltage across this diode will be equal to 0 volts. Okay, V forward, the voltage across the diode is equal to 0 volts. Since it is short circuited, the voltage across this diode will be equal to 0 volts. Vf is equal to 0 volts. Now, what is the current flowing through this diode? Okay, so how to find the current? That is If. Okay, the current flowing through this diode If is given by the Kirchhoff's law, or we can apply the voltage law. That is If is equal to V by R. We can also apply Ohm's law. If is equal to V by R. So from this If we can get, right, so V external divided by R. So V external, or also you can write as V bias. If is equal to V bias or V external divided by R. So this is the current flowing through the diode, or forward current flowing through the diode. How I found this equation? So this voltage is equal to the current into resistance. Okay, I into R. So I will be equal to V by R. That's it. I hope up to here it is clear for everyone. Okay, shall we move forward? So this is the ideal approximation of a forward bias current. Okay, and what is the current flowing through the reverse bias diode? That is IR will be equal to 0 amperes. So the reverse bias current, or the current flowing through a reverse bias diode, will be equal to 0 volts. Okay, there will be no current flowing through the reverse bias diode in a ideal approximation. Reverse bias current will be equal to 0. Okay, now what is the VR? Okay, reverse bias voltage. What is VR? So VR will be equal to simply V bias voltage. VR will be equal to simply V bias voltage. So I'll write it here. The reverse voltage VR is equal to V bias. V bias. So the reverse voltage will be equal to simply V bias, or reverse voltage will be equal to VR will be equal to V external. So this is the case of reverse bias diode. So these three cases are the cases of reverse bias diode. So this is how we are going to find the current flowing through the diode and the voltage across the diode by approximating the diode, by taking the help of diode approximation models. Okay, I hope this is clear. So this is how we are going to take the help of diode approximation models to find out the current flowing through the current and voltage across this diodes. Okay, so I hope it is clear. So if you are having any doubts or queries, you can ask me, or else we can end this session. Okay, so we'll discuss other two models in our next session, upcoming sessions. Okay, yeah, so that's all for this session. I hope you have liked this session. So if you like it, if you have any doubts or queries, you can you can comment in the chat, or else we can end this session. And don't forget to subscribe to our YouTube channel, and do browse more courses which are available in our YouTube channel. We have plenty of courses which are available in our on our YouTube channel. Okay, yeah, okay then, yeah, thank you.